Welcome to Chapter 19, Climate Change. Can you turn off the scrambling sound that I hear? Oh, there we go. Okay. So, fun fact for the beginning of this lecture that was brought to me by a student of mine who's actually sitting back there as I record this. In South America, in the Amazon River Basin, there is a very small population of very endangered river otters, giant river otters, that are 6 feet long. To make that impressive, that's a huge otter, by the way. I mean, it's bigger than Mr. Pooler, which is hard to believe. Your standard everyday otter that you guys are familiar with is approximately 1.5 feet to 2 feet long. This thing is 6 feet long, roughly 3 to 3.75 times longer than your regular otter. That's crazy. They form monogamous relationships. What? That's weird, right? So, male and female will stay together and have many litters of pups. And yeah, it just seems that's pretty cool, but I wouldn't want to run into one of them. So here we go. Climate change. Okay, what's important on this one? So the globe has been warming and cooling throughout Earth's history, and that is something that we know. And in fact, for the majority of the time the Earth has been in existence, there has not been any ice on it. Ice on the planet, snow on the planet, is a rarity. Right? For 4.5 billion years Earth has been here. About 3.5 billion years there hasn't been any snow or ice on the planet. So that's the norm. For about 1 billion years we've actually had snow and or ice, kind of like we do right now. So it's not the norm. And you can see here we've got a glacier, or not glacier, sorry, an impact zone where the dinosaurs, right? There was a huge meteor that landed. It sends out lots of dust into the atmosphere, blocks the sun's sunlight, cools down the planet momentarily. These are natural cooling trends that can take place. And you can see right here in Chile, there was a massive volcanic eruption. And when all that soot and ash goes into the atmosphere, again blocks the sun's lights, or sun's energy from reaching the surface of the planet, which then has a cooling effect. The Yellowstone National Park here in the United States is it's the biggest volcano on the planet. And when that erupts next time, and it erupts every 650,000 years, it will send up so much volcanic ash that it will cause a cooling trend for roughly 10 years on the planet. Pretty crazy. So we also got some volcanic eruptions, tectonic plates alter the climate on the planet, large meteors that we discussed. Good stuff, good times. So, in what ways are humans impacting the environment? Because right now it says, where is the next ice age, or the ice age? We should be in an ice age right now. We should have started going back into an ice age 4,000 years ago, according to the solar radiation that we receive right now. But we aren't. And here's one of the reasons. Around 8,000 years ago, we started agriculture. And that puts lots of carbon dioxide into the atmosphere because we clear land, we cut down trees to grow food. And that cutting down and burning of the trees releases lots of carbon dioxide into the atmosphere. About 5,000 years ago, we domesticated cattle, and cows release large quantities of CH4, which is methane. And you will need to know that CH4 is the chemical formula for methane gas, which is farts. Okay, so now cows have 4 ruminants, or 4 chambers in their stomach, so they burp a lot and they belch a lot. They also do fart a lot, but it's more of the belching from the breakdown of the food in their gut that releases the methane. And as of right now, cows are the largest emitters of methane gas that we have on the planet, more so than factories, industry, anything. So it's cows. And then growing rice also releases methane, because what we do is we flood an area, we put plants in there, and once we've done harvesting the rice, the rest of that plant sits in that water and breaks down. And those small shallow ponds get warm, so there's not a lot of oxygen. So you have these anaerobic, right, because there's no oxygen in there, and anaerobic bacteria breaking down the plant material, and that releases methane gas. And then in the Industrial Revolution, we started burning fossil fuels, which is ancient sunlight. Right? Fossil fuels are the product of the breakdown of plants on land and in the ocean, and they grew from the sun's energy millions of years ago, so it's often referred to as ancient sunlight. The oil that we burn right now is roughly 500 million years old. The coal that we use right now is roughly 350 million years old. So without this ancient sunlight, there's no way we could have gotten our civilization to the point that it is today. But continued use of it could be our demise as well. Dun, 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 dun. Global climate change. So let's talk global warming. First off, is an increase in the average temperature of the Earth's atmosphere and oceans, and it's caused by too many greenhouse gases. So first off, the greenhouse effect is something that is very, very important, because without the greenhouse effect, it would be too cold on planet Earth for life to survive. There'd be nothing living. It'd be too cold, too frigid. Now we have all these greenhouse gases, and I think we're going to put a list up here in a second that you have to be familiar with them. Now what they do is they form a blanket surrounding the Earth. So the sun's energy, we have a lot of high intense energy coming from the sun, right? X-rays, gamma rays, they hit the surface of the Earth absorbs them. And then what it does is it re-emits them as a longer wavelength, lower energy, known as radiant or heat energy. So the Earth absorbs the high intensity energy from the sun and then re-emits it as heat. Now as that heat is moving back out towards space, those greenhouse gases trap that heat, so it gets stuck around the planet, and that makes it warm enough for organisms, people, and things to survive. But too many greenhouse gases are going to make it too warm, and they're going to change the climate. So I hate to say global warming. I think climate change or climate destabilization is a better way to term it. So you can see we've got the north right now in an Arctic blast, so it doesn't feel much warmer up there. But the Arctic chills that we've experienced last year and this year are due to a weakening of the jet streams, which is a product of climate change. So it has an impact on many different levels. So human activities and CO2. Human activities emit greenhouse gases. We already talked about industrial revolution, right? Burning fossil fuels to release carbon dioxide. CO2 and methane from agriculture, deforestation, cows, rice, and N2O, which is a type of NOx that we'll talk about later on, and air pollution, which comes from the burning of fossil fuels. Our CO2 is increasing exponentially because as our population explodes, the need for energy for all those people also explodes and increases. At current rates, the CO2 will rise to 1,390 ppm, that's parts per million, by 2100, so at the end of the century. And the tipping point for runaway climate change, where we can't stop any of the effects, is 450 parts per million. So as you can see, we really got to curb this. Right now I think we're at 378 on average, something like that, parts per million. And if we continue with this trend of CO2 release, as our population continues to expand exponentially, then we'll be way past the tipping point by the end of the century, which is very scary. So who releases most of the CO2? The United States takes the lead. Number one, we release 25% of it. And at a population of 325 million people in the US, the per capita or per person release is massive, much bigger than any other country. The European Union is a big emitter, Japan. So between the European Union, which is 27 countries, those 27 in Japan account for 65%. We account for 25%. And what about China? They account for roughly 5% of the CO2. Now that's going to increase dramatically as more and more of their population continues to become industrialized, becomes more affluent. They're going to start burning through even more coal than they already do and other fossil fuels and natural gas. So the rapid increase in economy began, China for a long time didn't produce any CO2. Now they're producing 5% of the world's CO2. Shortly, they're going to be up there with us as far as how much CO2 they produce. So why such a rapid increase? It began when we, in the 1980s, persuaded them to build all of our crap for us for cheap. We were a product country for a long time, right? And then we decided to move beyond that and become a service market, so we don't really produce any of our own stuff anymore. And we wanted to produce a lot of it very cheap, so we used third world or developing countries to do it for us at cut rate prices, which really increased the quantity of CO2 they release. And what fuel powers China? It is coal, 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 coal. They're building 2 new coal-fired power plants every single week. That is huge. They burn, and their coal is a very, very dirty type. Thank you, Miss Natalie. You can see it right there. Wonderful day. The coal they burn is so dirty that in Beijing, last year there was a fire in a factory that burned for 3 hours. 3 hours. And nobody knew that the factory was on fire because they couldn't differentiate between the smog already there and the smoke as a product of the fire. That's crazy. All right, moving on. So evidence of climate change. We can look at these different things. We'll go through them one by one. Tree rings, increased CO2 levels across the world, changing seasons, ice cores, the melting of ice caps, poor circulation of our ocean currents. So let's start with number one. Tree rings will give us the history of climate back to 9,000 years. They take a core out of the tree and they can look back and see these wide light-colored rings are for the growing season in spring. The dark rings are the winter and fall. So if you count one color, either the light bands or the dark bands, you can age a tree. So we can go back in time and look at the climate by counting back through these rings. Now we don't have trees that are 9,000 years old, but we do have trees that have been buried and preserved that we can take cores out of and look back at them, and we've developed a timeline going back 9,000 years. And we found throughout that time that carbon dioxide is increasing. And because carbon dioxide is a fuel for trees, we have seen some good growth out of trees recently. So the white bands in certain areas are getting thicker. So let's look here at this little graph. This is CO2 concentrations going back the last 400,000 years. So we can go back 400,000 years, not even farther. Well, I'll tell you how in just a little bit. And this is the temperature going back 4,000 years. And if you look at the CO2 graph and you look at the temperature graph, they look very, very similar. There's a correlation between the two. And if you put one on top of the other, there is quite a dramatic correlation between the two. So what we see is that as CO2 concentrations increase or decrease, temperature follows that increase or decrease throughout time. And right now, the CO2 concentrations have skyrocketed exponentially to right here. And now we're just waiting for the temperature to follow suit. So we have changing seasons. The winters are becoming shorter. The summers are becoming longer. There's something else that goes with that. I'm trying to remember. Oh yeah, so there's things right here showing things that are blooming. In Florida, azaleas typically bloom in late March, early April. The last 3 years running, they've been blooming in January. Right? That's months earlier than they should. The migrations of animals are changing. Animals are actually migrating earlier because they're getting those warming signals earlier, so they actually leave and migrate earlier, and that may seem like not a big deal. But sometimes there are migrations that need to be timed perfectly. There's a species of bird that flies across the entire Pacific Ocean, and they can't make it across the entire ocean, and there's no island for them to land on in certain parts. So it just so happens that horseshoe crabs into the Pacific Ocean come to the surface of the ocean to spawn and breed at this certain time. So these birds actually land on an island of horseshoe crabs that's created by them all coming to the surface, and they eat the eggs that float around in the water. Now the spawning action is a 2-week process. So if these birds change their migration pattern by just 2 weeks, then they'll never make it across the ocean, and they would die from exhaustion before they ever made it. So it's very important that we don't change these things, the seasons, too much. Ice cores. Just like a tree core, we drill a cylindrical core through the ice, and we look at the bands. The dark bands tell us that this is like the cold seasons, right? So this is the winter in the Arctic, and this in the thin lighter band, it would be like the summer and spring in the Arctic, right? And we can look at how thick the bands are to figure out how much accumulation there was during that time frame. More importantly, what we can do is we can go into these ice cores. And see, there's another picture right here. You can see these pockets, these bubbles, right? And this is preserved atmospheric gas from the time this ice was frozen, when it was made. And so we can drill in there and we can extract that air out of there, and we can look at CO2 concentrations, oxygen concentrations, and whatever other gas was in the atmosphere at the time. So we can tell exactly what the air composition was in these bubbles during this time frame. And that takes us back 740,000 years. We can tell you exactly how much CO2 was in the atmosphere. Amazing. Ice caps are melting. This is the boundary of the Arctic ice cap in 1979. This is roughly where it is now and getting smaller. Greenland is melting dramatically. This is a freshwater river that's opening up in this piece of ice on top of Greenland, and what happens is sometimes it meets obstacles and it starts to pool up, and eventually that moving water churns and drills a hole through that ice all the way down to the bottom, to the land underneath the glacier. And what they're worried about is all that water going down underneath the glacier is eventually going to lubricate a large chunk of it, right? Because it puts positive pressure in between the earth and the ice, and it will break it off and just cause it to flow into the ocean. And since this ice is not in the water, it's not yet accounted for in the volume of the ocean. So that much fresh water going in would raise the sea levels dramatically. When all this ice is gone, ocean levels will be 20 feet higher than they currently are. So why do we need ice besides keeping our coastlines where they are today? The ice is very reflective. This reflectivity of a surface is known as its albedo. So when the sunlight hits the ice, it reflects off of it and goes back into outer space, and it keeps the oceans from absorbing that heat. The less ice we have, the more sunlight hits the Earth's oceans, and the oceans absorb that heat energy and hold on to it, and the oceans get warmer. As the oceans get warmer, more ice melts. Less ice means more sunlight hitting the oceans get warmer. The warmer oceans melt more ice, and so on and so forth. So we get this blank feedback loop. What is it? Positive, good, give yourself a pat on the back. Positive feedback loop that just exacerbates the situation. So can the oceans save us? The oceans do help moderate temperatures because they absorb carbon dioxide, tremendous quantities of carbon dioxide. However, as the warmer the oceans get, the less CO2 they can hold on to, right? Think about it with your soda. If you take a soda, 2 different sodas, open one up, put one on your kitchen counter, open up another one, put one in the fridge, the one that's left on the counter will lose all of its carbon dioxide much faster than the one in the fridge, because gases stay trapped or dissolved in liquids much better when the liquid is cold. So the warmer the oceans get, the less CO2 they can hold on to. So eventually, all the CO2 they've absorbed over the years and years, they're just going to burp it into the atmosphere at some point in time. When? We don't know. So is there consensus on climate change? This is perhaps the most important part. When you talk to the scientists who have done the studies, there is no question about it. I heard one of a well-known climatologist who did a lot of these studies that this information comes from, say that when he goes to colleges, he tells people not to go into climate science anymore because we already know what we need to know. Go into other types of sciences where you can have an impact, but don't study climate science because we already know what we need to know. Climate change, anthropogenic, human-induced climate change is happening. All right, so 2,500 studies done in 130 different countries, and the consensus is yes, anthropogenic or human-induced climate change is taking place. The only time that it's at all discussed as perhaps not being a real thing is in politics. And we need to separate politics from science so we can understand what's happening. So a little additional information on CH4, because it's also a big concern. It comes from cows, we already said, rice, and dams. Think of dams and rice produce methane the same way. You build a dam, all the vegetation that was on the land before it was flooded by building the dam is now underwater. You have anaerobic bacteria that break down that vegetation. In the lack of oxygen, the product is not carbon dioxide, but the product, because there's no oxygen in the water, right? So you can't make CO2. The product becomes methane gas, CH4. So dams produce lots of of methane. But we have lots of permafrost in China, vast quantities, millions of square miles of permafrost that is melting. And you create this mushy ground. Again, no oxygen, bacteria in the water breaking down organic material in this melting permafrost mush creates lots and lots of methane. Right now there's an ice cap layer over all this methane gas that's trapped in this permafrost. And when that ice cap melts through or thins out, it's going to belch or fart out, a giant Russian fart, all of this methane gas in the atmosphere. And that's scary and a concern because each molecule of methane gas can trap 23 times more heat energy than each molecule of carbon dioxide. Whew. Scary. All right, so that's it for 19.1.